All right, diving right in today, we're tackling a real classic, one of those computer science debates that just never gets old. Threads versus events, or
Ooh.
high concurrency servers, those things that going to handle like a zillion requests every second. And we've got this paper straight out of 2003 USENIX conference.
Right.
Really shakes things up. And that's what we're going to unpack today. So
Okay.
buckle up, get ready to untangle the arguments for threads, for events,
Yeah.
see if we can bust a few myths along the way.
It's a big debate for sure. I mean, it really affects how our software performs in the real world.
Oh, absolutely. So to set the scene right, for the longest time, event-based programming was like the king, the champ for building these crazy fast scalable servers.
Oh,
But
yeah.
why? Why was that the go-to? Well, the paper lays out four main arguments in favor of events.
Yeah. So the first one they bring up is inexpensive synchronization.
Okay.
A lot of event-based systems, they lean on this idea of cooperative multitasking, where tasks politely hand off control when they're done. So you don't need all these complex locking mechanisms.
So it's like instead of those threads all fighting over resources, it's more like after you, no, after you.
Exactly. It's very polite. And this leads right into the second advantage, low overhead.
Okay.
Because you're not dealing with these big, bulky thread stacks, event-based systems. They stay super lightweight.
Which means more resources for the stuff that matters. Handling those requests makes sense, all right? What else makes events so appealing?
The third big one, smarter scheduling in event-based systems. The application itself gets to decide what to do next,
Oh.
instead of relying on the operating system scheduler.
So it's like having this internal traffic cop that just knows exactly where every request needs to go.
Exactly. They've got it all mapped out. And then finally, you've got flexible control flow.
Okay.
You're not stuck with that traditional call and return pattern, with function calls.
So you've got options.
Exactly.
All right, so events, they make a pretty compelling case, right?
Yeah.
But now comes the plot twist. This paper comes in, throws a curveball and says, hold on, threads can do all that too.
Uh-huh.
And maybe even better what? What makes them think that?
Well, they claim that a lot of the problems that people associate with threads, they're not really problems of the concept itself. It's more about
Okay.
specific implementations, how they've been done in the past.
So it's not the tool, it's the worker.
Exactly. You got to know how to use it, right?
Yeah.
They actually went and redid a famous benchmark from the SETA paper, that one all about staged event-driven architecture.
Oh, yeah.
And they used a modified user-level thread package.
So they're putting these threads to the test against a classic event-driven system head-to-head.
Yep. And the results were pretty surprising.
Oh, really?
They got performance just as good as the event-based server, even when they scaled it up to 100,000 threads.
100,000 threads, that's a lot of threads.
It is.
So how'd they manage that? What's the secret sauce? Is it just about smart implementation or is there something more to it?
It's a combination of things. One of the key arguments they make is that threads actually offer more natural control flow, especially for the kind of servers we're talking about.
Okay.
Lots of independent requests, but the code itself is mostly sequential.
Okay, so why is that sequential control flow better in this context?
Think of it like following a recipe.
Okay.
With threads, it's like you're going through each step one by one in order.
Right.
With events, it's more like you're juggling all these ingredients in the air. At the same time, it gets a little messy.
Okay. I can see the analogy there. So threads give you more structure.
Yeah, a more organized way to deal with all those requests.
Yeah, but what about those stack issues that threads are notorious for, the risk of overflow or just wasting space?
That's a good point. That's a real concern.
Yeah.
But they have a solution, dynamic stack growth.
Okay.
Imagine the compiler could actually analyze your code and figure out when the stack needs to get bigger.
Oh, so like giving it an elastic waistband.
Exactly. You got it, and that way you avoid those fixed stack sizes and all the problems they bring.
That's pretty neat. But wouldn't all that resizing add some overhead? Wouldn't that slow things down?
That's a good question, and it's something we're going to dig into more when we look at how they actually implemented all this.
All right, so for now, let's keep going with those arguments in favor of threads.
Sounds good.
What else do they have up their sleeve?
So another common criticism of threads is that they can make programmers a little lazy
Okay.
about managing live data, the stuff that's actively being used.
Right.
But again, they've got a solution for this.
More compiler magic.
Yeah, basically they envision this super smart compiler
Okay.
that can help purge unnecessary state from the stack and even warn programmers if they're holding on to too much stuff.
So the compiler's like this very tidy housekeeper, keeping things nice and efficient. I like it.
Exactly.
Okay, so what about the argument that event-based systems, they have it easier with synchronization because of that cooperative multitasking we talked about?
Right, that's a common claim, but the paper points out that cooperative thread systems can do this too.
Oh.
And it really only works on single processor systems anyway.
So not a universal advantage.
Nope. And then they hinted something really cool.
Oh, what's this next level of awesomeness?
They suggest that compilers could actually play a big role in synchronization on multiprocessor systems,
Ooh.
which is where things get really tricky. But we'll save that juicy bit for later.
Okay, you've definitely got me hooked. So far, we've heard about how threads can handle control flow and state management, maybe even better than events.
Yeah.
And with a little help from our friend the compiler, but these guys, they didn't just talk the talk, right? They
Right.
actually built something.
Yeah. They put their money where their mouth is.
So they developed their own thread package and web server.
They called it Not.
Not clever.
Yeah, and they tested it head-to-head against Haboop,
Okay.
the event-driven server from that SATA paper, remember?
Oh, yeah. So Not versus Haboop, a real showdown. What happened?
To put them through their paces, they used a benchmark that's specifically designed to stress test web server performance.
Yeah.
They looked at bandwidth CPU usage, how often those context switches were happening.
Okay, so they really put them through the ringer, all right? So what happened?
Both Not and Haboop showed the same basic trend as the number of client requests went up, bandwidth climbed until they hit their max capacity.
Right, so they both have a limit, which makes sense, but did one of them reach a higher peak? You know, was there a clear winner in terms of how much they could handle?
Actually, Not hit a much higher maximum bandwidth than Haboop.
Really? By how much?
Almost 700 megabits per second compared to around 500 for Haboop.
Wow, okay, so Not's pulling ahead here, but what about those other things? The CPU usage and the context switching did not maintain its lid there, too.
That's where things get really interesting. Haboop actually became CPU bound much sooner than Not, meaning it was using more processing power to handle the same workload.
Oh, wow.
Okay,
Oh,
and then when it comes to context switching, Not was way more efficient,
okay.
switching between threads a lot less frequently.
So not only did Not deliver more, it did it using less and switching less. That's impressive. Why was Not so much better at this? Is it just down to better implementation, or is there something fundamentally different about how it does things?
The authors point to a few key factors, and that's what we're going to dive into in the next part of our deep dive.
You're killing me here. All right, everyone, stay tuned, because in part 2, we're going to dissect those reasons behind Not's impressive performance and uncover those specific implementation choices that made all the difference.
We'll also explore that intriguing world of compiler-assisted synchronization and what it could mean for the future of how we write concurrent code. Don't miss it.
It's going to be good.
Welcome back to the deep dive. So let's unpack this. Why did Not this thread-based server do so well in those head-to-head tests against Haboop?
Yeah, you left us hanging, revealing that Not aced those benchmark tests, flying colors, higher throughput, lower CPU usage, fewer context switches. What's the secret sauce?
Well, the authors, they point to a few really clever design choices. First, remember that dynamic stack growth we talked about.
Right, the compiler figures out when to expand the stack so you don't get those nasty overflows. But how does it actually know when more space is needed? That sounds pretty tricky.
It is. The compiler would have to analyze the code's structure, right? Identify functions that might have deep recursion or, use a ton of local variables.
Okay.
And then it would have to insert instructions to dynamically allocate more stack space as needed.
So it's like giving the stack an elastic waistband so it can stretch without breaking?
Yeah, exactly. You got it.
Okay. But wouldn't all that resizing add some overhead? I mean, wouldn't that slow things down?
Yeah, that's a valid point. They do acknowledge that dynamic stack growth does add some overhead,
Right.
but they argue that it's way less than the overhead you get from either having these fixed oversized stacks that just waste memory,
Okay.
or the risk of those stack overflow errors that can just crash the whole system.
Right. So it's a trade-off, but they're saying it's a good one.
Exactly.
Okay, so dynamic stack growth helps Not manage memory efficiently. What other tricks did they use to squeeze out that extra performance?
Another key factor is how Not handles blocking operations. Things like waiting for data from a disk or a network connection.
Right.
In a traditional threaded system, if one thread gets stuck waiting, he can hold up a whole process.
Like a traffic jam on a single lane road?
Exactly. But Not uses this technique called asynchronous I/O.
Okay.
And this lets threads keep doing other work while those slower operations finish up in the background.
So it's like having a separate lane for those slow pokes so everyone else can keep moving.
A perfect analogy.
It's pretty neat. So Not manages memory well. It avoids those blocking issues. Anything else contributing to its stellar performance?
You know how we talked about events sometimes leading to more complicated control flow?
Yeah, yeah.
Well, that can make it harder for the compiler to optimize the code.
Right, because the compiler has a harder time following those tangled paths.
Exactly.
Oh,
And that can impact performance, but not on the other hand, it benefits from that more straightforward thread-based control flow.
okay.
And that makes it easier for the compiler to do its magic.
So threads are more compiler friendly in a way.
That's interesting. What about garbage collection? Isn't that a big performance factor, especially for these high concurrency servers?
Oh, you're absolutely right. Garbage collection can be a real bottleneck. Haboop, the event-driven server, it relies heavily on garbage collection to manage memory. And
Yeah,
that can lead to those pauses where everything just grinds to a halt.
like hitting those random speed bumps on the highway.
A very apt description.
Yeah.
Not, though, with its more careful state management.
Yeah.
It can minimize those garbage collection pauses, so you get smoother, more consistent performance.
Okay, so we've got dynamic stack growth, asynchronous I/O, compiler-friendly, control flow, efficient garbage collection, all these things working together to give not that edge in this server showdown.
Oh.
But I keep thinking back to those hints about compilers and synchronization on multiprocessor systems. Is that where this is all headed?
It is. The author suggests that compilers could play a much bigger role in helping us write thread-safe code, especially in that complex world of multi-core processors. But how could a compiler possibly understand all the intricacies of concurrency, and prevent those tricky race conditions where multiple threads are trying to access the same data at the same time?
It's a tough problem, for sure, but they envision a compiler that's way more sophisticated than what we have today.
Okay.
It would analyze our code for potential concurrency issues, insert synchronization primitives where needed, even guide the thread scheduler for optimal performance.
So it'd be like having a concurrency expert built right into the compiler, always watching our backs, preventing those disastrous data collisions.
Exactly.
That's pretty mind-blowing. It would make concurrent programming so much easier and less error-prone.
But are we getting a little ahead of ourselves here? Is this even technically feasible?
It's definitely a long-term goal, but there's been a lot of promising research in areas like static analysis and formal verification.
Okay.
Researchers are developing tools that can automatically spot potential concurrency bugs and even prove that concurrent code is correct. So it's not just science fiction. It's an active area of research with real potential to change how we build software.
Absolutely.
Yeah.
And if we could really harness the power of compilers to manage concurrency, it would be a game changer.
Yeah, I'm starting to see why the authors are so excited about this. It opens up a whole new world of efficient and reliable concurrent programming. But let's not get lost in the future just yet.
Right.
Before we wrap up, I want to make sure we've connected all the dots,
Sure.
Why is this research so significant? We've seen how well-implemented threads can compete with even beat event-driven systems, but what's the bigger picture here? What does this mean for the future of how we build software?
That's a great question. I think this research really challenges some of the assumptions we have about threads and events.
Yeah.
It shows that threads, which are often seen as clunky and inefficient, can actually be incredibly powerful when they're used thoughtfully.
So it's not about blindly choosing one over the other. It's about understanding the strengths and weaknesses of each approach and picking the right tool for the job.
Exactly.
Yeah.
And maybe even more importantly, this research highlights the potential of compilers.
Yeah.
Imagine a world where the compiler becomes our partner in concurrency,
Oh,
helping us write code that's not just fast and efficient, but also inherently safe and reliable.
it's a pretty amazing vision of a future where all that complexity of concurrency is just handled for us,
Yeah.
So developers can focus on building awesome applications without getting bogged down in all those low-level details.
And that's a future worth striving for.
Absolutely. Well, folks, we've covered a lot of ground in this deep dive. We've seen that epic server showdown, we've debunked some myths about threads, and we've even glimpsed into a future where compilers become our concurrency allies. But there's one final piece of the puzzle we need to explore.
Ah, yes. The question that should stay with you long after this deep dive is over.
Stay tuned for the final part of this episode, where we'll leave you with a thought-provoking question that might just change how you think about the future of software. All right, we're back for the final part of our deep dive into this world of threads events and the future of concurrent programming.
We've seen how threads can actually be super efficient, right? Even beating those event-driven systems in certain situations.
Yeah.
And we've touched on that idea of compilers becoming these powerful allies in managing concurrency.
Right. It's been a wild ride. But before we wrap things up, we wanted to leave you with a question.
Yeah, something to really think about.
As you navigate this ever-evolving world of software development.
A question that goes beyond, the specifics of this one paper
Yeah.
and digs into the bigger implications of what we've been talking about.
So here it is. What if concurrency wasn't this big, scary thing that only the most experienced programmers could handle?
Right.
What if the tools we use, like compilers, could take care of all that complexity for us?
Yeah.
So concurrent programming would be easier, more intuitive, and way less error-prone.
Imagine a world where any developer, no matter their experience,
Right.
could easily harness the power of multi-core processors
Yeah.
without having to worry about those nasty race conditions and deadlocks.
What if writing concurrent code was just as straightforward as writing sequential code?
Yeah,
What kind of impact would that have on the software we build?
that's a pretty exciting thought, right?
Yeah.
We could see this huge burst of innovation in areas that depend on concurrent processing.
Yeah.
Things like scientific computing, machine learning, AI,
Mm.
even game development.
We could build systems that are not just faster and more efficient,
Right.
but also more robust, more reliable, because those concurrency bugs that are so hard to find would be gone.
It would truly democratize concurrency,
Yeah.
giving developers of all skill levels the power to build amazing applications that use the full potential of modern hardware.
Think about it. More responsive user interfaces, more immersive VR experiences, more sophisticated simulations,
Yeah.
maybe even entirely new types of software that we can't even imagine yet.
Of course, this vision of a concurrency utopia,
Mm.
it's not without its challenges.
Right.
Building compilers that can truly manage concurrency, that's a tough problem.
Yeah.
It requires big leaps forward in things like static analysis, program verification, compiler optimization.
But the research is moving in that direction.
It is.
We're seeing new tools and techniques that give us reason to be optimistic about the future of concurrent programming.
And as we move towards that future, we have to keep asking these questions.
Yeah.
Keep challenging the status quo. Keep pushing the limits of what's possible with software.
So as you go on your own coding adventures,
Yeah,
think about this. What would you build if concurrency wasn't a barrier anymore?
right.
What could you create if you could use the full power of multi-core processing without those concurrency demons lurking in the shadows?
Let that question fuel your curiosity. Keep exploring this fascinating world of concurrent programming.
And remember what the authors of this paper have shown us. Even those long-held assumptions can be challenged. And those groundbreaking innovations, they often come from questioning the conventional wisdom.
Exactly.
Well, that wraps up our deep dive into threads versus events.
Yeah.
We hope you've enjoyed exploring this classic computer science debate with us.
Yeah.
And we hope it's made you curious about the future of software development.
Until next time, keep coding, keep learning, and keep pushing those boundaries.
See you next time.